So we're going to introduce a different way of writing complex numbers known as Mod-Arg Form. So modulus is something you already know. It's basically the length or the magnitude of a vector. So there's the complex number z equals x plus iy. If I join it up to the origin and create the vector, the position vector, then the modulus would be the length. So basically it's just the distance from the origin, or another way of thinking about it, the absolute value. It's the same as that as well. And we could work it out quite easily because we know in that right angled triangle the base there is the real part, the height would be the imaginary part. So we could work it out to be the square root of x squared plus y squared. So r, or the other notation we often see, or probably more commonly see, for modulus is just the absolute value symbol. So there it is. Mod z is equal to the square root of x squared plus y squared. And then we have this thing called the argument, and that's like the direction of the vector. So if that angle in there, theta, which is the direction of the vector, we call the arg, or the argument, of the complex number. Okay, so it will be the inverse tan of the imaginary part over the real part. And we always define, similar to what we did in vectors, same idea, we'll always define that angle to be either positive acute or obtuse or negative acute or obtuse. In other words, they go between minus pi and pi, or minus 180, 180. Notice the minus pi is not included, because pi and minus pi is the same position, and we want to make sure we have a definite answer, so we always go with positive pi rather than negative pi. So if we had the complex number 4 minus 4i, then the modulus we could work out, real part squared plus the imaginary part squared, that turns out to be 4 root 2. The argument, now with the argument, just like with vectors, we have to be very careful. Because remember, our calculator will only give us specific answers. We need to know exactly where the location is. And that's why I've written this as negative 4 over 4 rather than negative 1. Because negative 1 will give me a specific answer. But if I draw the diagram, negative 4 on 4 allows me to locate the position exactly. We know that the imaginary part is negative, the real part is positive, so I must end up with a negative acute angle. We're in that fourth quadrant, and so it'll be minus pi on 4. Now I think that's fine, the calculator would give us that answer, minus pi on 4. But imagine we were over in the second quadrant, where it was the other way around, where the imaginary part was positive and the real part was negative. Still going to give us an answer of negative 1, so the calculator would still give me the answer of negative pi on 4, but in reality it would be the obtuse angle of 3 pi on 4. So that's why it's important to locate exactly where it is that you're talking about. So each of our complex numbers can be written in terms of its modulus and its argument. So z equals x plus iy, we know that, but now we could rewrite it, because using that right angle triangle, I could work out that x is equal to r times the cosine of theta. And y would end up being r times the sine of theta. R is a common factor, so we could take it as r outside of cos theta plus I sine theta. So Mod-Arg form is that, when we're writing in terms of its modulus and its argument. So r cos theta plus I sine theta. You'll sometimes see it abbreviated as cis, because the angle doesn't change. It's the same theta in both the cos theta and the sine theta. Just be very careful if you're going to use that cis notation, because it is so easy to write cos instead of cis, or cis instead of cos. So you just need to be aware of that. Be very careful. So r is the modulus and theta is the argument. So back to our 4 minus 4i, we've already worked out the modulus of the argument. If I put it in cis notation, I'd say, well, that's 4 root 2, the cis of minus pi on 4. Root 3 plus I, you'll see these ratios, the exact ratios, coming up a lot. So obviously we know the exact values for them. So the modulus of that one is 2. The argument, 1 on root 3, they're both positive, so I must be in the first quadrant. So I'm looking for an acute angle here. So we get pi on 6. So that would be 2 cis pi on 6. Now, if I was going back the other way, that's where it's important we remember what cis actually stands for, because we can just expand it out. Remember, cis is actually 6 times the cosine of pi on 6 plus I sine pi on 6. Pi on 6 is 30 degrees, isn't it? So cos of 30 is root 3 on 2. Sine of 30 is a half. Expand that out and we get our answer. 3 root 3 plus 3i. So converting between the two is a fairly simple process. Okay, some relationships then that we can use in our arithmetic. It does not matter the order that you find the modulus. You could multiply the two complex numbers together first, then find the modulus of the answer, or you might find it easier to find the modulus of each individual complex number and just multiply those answers together. When it comes to arguments, however, we're adding. So argument of z1 times z2, we would add the two arguments together. Okay? And that's all to do with, do you remember when we first looked at the Argand diagram and I said multiplication by I was a rotation of 90 degrees. And every multiplication by I is another rotation. See, multiplication is a rotation. So therefore it's like adding the angle on because you're rotating it a further so many degrees. Let's prove it. Okay, so I've got two complex numbers, which I'll just call Z1 and Z2. If I was to multiply them all together, well, the modulus one's easy enough because I can just pull those out together and I get the R1, R2. But the rest, a bit more work. So let's expand the parentheses out and we get cos theta 1 cos theta 2 plus I sin theta 1 cos theta 2 plus I cos theta 1 sin theta 2 minus, because of the I squared, sin theta 1 sin theta 2. Let's group the real and imaginary and you'll see something familiar happening there. Cos cos, sin sin. If it's not the sine, it's not the sine. So there's our first one. But look at the second one. Sin cos, cos sine. If it's the sine, it's the sine. So we end up with the cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. The angle is the same. So yes, that is R1, R2, the cis of theta 1 plus theta 2. So yep, it works. Excellent. So then logically follows, if I had several things multiplied together, Z1 times Z2 times Z3 times Z4 and so on and so on and so on, I could just multiply each of the individual moduli together to work out the modulus of the answer. And with the arguments, I would just add each of the individual arguments together to come up with the answer. Okay, division, we see a similar thing happening. Division, doesn't matter. We could do the division first, then find the modulus, or find the modulus of each individual bit, then do the division. And with this one, it's a subtraction rather than a division. And again, that's all to do with the rotation of the angles. So it now logically follows is, if I've got some mixture of multiplying and dividing complex numbers together, well, the moduli just follows the same pattern. Z1's times Z2, so we can do that on the top, and on the bottom we can do the Z3 times the Z4, that works. When it comes to the arguments, well, whatever's on the top of the fraction would have a positive argument, and then whatever's on the bottom would have a negative argument because we're dividing by that. So I'd go argument of Z1 plus argument of Z2 minus the argument of Z3 minus the argument of Z4. Which then brings up a really important one, which we'll see in more detail later. But if I'm raising a complex number to the power of n, then the complex number, z to the power of n, the modulus of that, I'll just find the modulus of z, raise that to the power of n. But when it comes to the argument, then I'll just go n arg z. This is really similar to something we've seen elsewhere, where division we subtracted. N, I'll just multiply it by n. What is that feature that we've seen? Logs. Now, and it's all to do with the exponential function, which we'll see later when we look at what's called Euler's number. All right, so let's find the modulus and the argument of this. Well, yes, I could go and work out that whole calculation, but it's going to be easier to do each individual bit. So the modulus would just be the modulus in the same pattern. So 5 plus I, 5 squared plus 1 squared, minus 2 minus I, so 2 squared, 1 squared, and then on the bottom of the fraction, square root of 3 squared plus 2 squared, and that all tidies up. Oh, isn't that lucky? Look at that, 13 goes into 26. Amazing how numbers work out. We just get root 10. So we know our answer would have a modulus of root 10. Unfortunately, the argument's not going to work out as nice because I didn't pick exact values here. So we'll have whatever the inverse tan of a fifth is, plus inverse tan. Again, notice I've written it as minus 1 or minus 2 to highlight to myself, hang on, I'm over in the third quadrant for this one. And then it'll be minus the inverse tan of 2/3. I've reverted to degrees here rather than radians, but 11 degrees 19 for the first one. There must be a negative obtuse angle in the third one. So we get minus 153 degrees 26, and then we're taking away the 3341, so negative 175.48. So we could work out our new complex number by going, oh, well, that's going to be root 10 times the cosine of this angle plus I times the sine of this angle. It'll be an approximation, of course, because we didn't end up with a nice, neat, exact number, but it'll get us pretty close to what the answer should be if we needed to. What happens if we shift the reference point? Now, we've seen this idea before with our graphs. Instead of the origin being the reference point for our graph, we shift it somewhere else. So, for example, x minus 1 all squared plus y minus 2 all squared equals 1. It's like, well, I've got my centre and moved it from the origin, and I've shifted it to 1, 2. But it's still the same circle. Well, we can do exactly the same thing in the Argand diagram. There's z, x plus iy. Now, if I think of it as a vector, remember its length is the modulus of z, and the angle it makes would be the direction of that position vector, OZ. Well, w over there is a plus ib. So it's no longer with reference to the origin. If I think of it as a vector, it's exactly what we saw in vectors. It's simply head minus tail. So if w is a minus b, that vector there, the length would be the modulus of z minus w, because that vector representing head minus tail, z minus w. And the angle is still the angle it makes with the horizontal, just like we saw with vectors as well. 1D will do us for today.